Hey guys, back today for another video. So today we're going to be doing cross layer equalization. It's a really old quantization technique, which is a weird thing to say because quantization hasn't been around for so long. But yeah, it's from like 2019 from Qualcomm. But before we get started, hey, if you're new to the channel, my name is Oscar Savalainen. I do a lot of AI stuff, particularly a lot of like neural network quantization stuff. And today we're going to be talking about, cross layer equalization. What is it? And how do we use it? And kind of, I'm going to be going through some code that I wrote for this, so it'll kind of make cross-layer equalization easier for you. But yeah, so just so we get started, I guess I'm gonna go over the original paper, which is written by Nagel et al. Or like Qualcomm. They are like fantastic quantization researchers. If you're ever looking for even just to get started with quantization, their white paper is fantastic. But yeah, they're considered like world experts at quantization basically. And so if we look at the paper, if we look at this paper, it's called data-free quantization through weight equalization and bias correction. There's actually two techniques in this paper, and they presented it as a data-free method for quantizing your networks. And the first technique that they're going to use is called cross-layer equalization, which they refer to as weight equalization, and then bias correction. I'm not going to be talking about bias correction today. I might have a separate video on it. Bias correction is a little bit out of date. A little bit. Most people use Adaround these days, also by Qualcomm. But bias correction is a pretty cool technique, but it's pretty much separate to cross-layer equalization. You can implement one, you can implement the other, but they're separate. So I'm just going to be talking about cross-layer equalization in this video. I'm not going to read through the entire paper. I'm just going to kind of skip to the part that's relevant to cross-layer equalization. But the fundamental idea is that, particularly if you're doing like per tensor quantization of weights, which normally you won't do, normally you'll do per channel, but you can plot out the dynamic ranges of your output channels of any given layer, and you might see some big mismatches in dynamic range. And so the idea is, well, okay, if you're quantizing this on a per tensor level, that's pretty bad. You don't want to see these massive outliers. You want everything to basically be uniformly distributed. That's going to minimize your quantization error, so to speak. And so they did this for a MobileNet V2, and they were looking at some of the layers, and they found that, okay, yeah, this massive has this difference. This doesn't matter as much for per channel quantization, because on a per channel basis, you just quantize each one of these individually, but maybe it's having some effect on the activations, equalizing them in some sort of way. And if you're quantizing your activations on a per tensor basis, this might actually be having an effect. So in the paper, they say that, hey, even if you're doing per channel quantization of weights, you might want to check out CLE anyway. And in case you do, I make this video for you. But the fundamental idea of CLE really is if you have two layers that are adjacent to each other, and we're going to call these layers with W1 and B1, so weight and bias, and then same thing for the second layer, the layer afterwards, which we're going to call W2 and B2. And if we have W2 and B2 kind of wrap W1 and B1 because it happens afterwards, so it takes the output of this and it feeds it into the input of W2. There is this world where, okay, we have the weight tensor for the first layer, we have the weight tensor for the second layer. We can actually implement a scaling on a per channel basis for all of the output channels of the first layer and the input channels of the second layer, such that they are actually equivalent, and they just go over it in this equation. It's actually pretty simple. So yeah, just like you can divide the output channels, and you can multiply the input channels of the second layer, and it all actually comes to the same. And then that's really just the fundamental insight of cross-layer equalization. They talk a little bit about how, like, even if you have reloos, you can kind of ignore the effect of a reloo because the kind of scaling still works in the same way. And I think they mention here that you can also do it for preloos. But yeah, as long as you just have like a basic activation in place, you can kind of keep this kind of scaling process going. All right, so this is the Jupyter Notebook that I mentioned. And so yeah, we're just going to kind of go over the code and see how it works. So there's just a bunch of imports. Not very relevant. We're going to be working on a ResNet 18 model, so yeah, that's just initializing and loading that in and getting the pre-trained weights. I mentioned that I did some FX stuff, so the cross-layer equalization API from PyTorch is an eager mode API, and it expects us to feed in the model, but also a list of lists. And each sublist in this list of lists is going to represent a pair of modules. So, like, in the case of that paper, it'll be like the first layer and the second layer, and it's just the pairs that we're going to do cross-layer equalization between. And This can all be run in eager mode, that's perfectly fine. But then you have to manually create that list, which I consider to be kind of a pain. It's one of the things I don't like about eager mode. And so what I did is that I used kind of an FX mode hack to kind of, well, it's not a hack, it's a technique, and like it works, but like it's the idea is that, hey, you first actually FX trace the model, and you use that to kind of step through the graph, and you identify these are the two layers that should have CLE done between them. These are two layers that have CLE done between them, etc. So that's what we do here. We symbolically trace the model, then we just fuse the batch norms into the convs. This is something I often do when I'm quantizing. And then, yeah, this is where we go through the graph. We find basically all of the different modules that have weights, and then we try to find, is there a previous layer that we could do CLE with? And it just has to meet a bunch of conditions. Like, it has to be either of type conv2 or linear. You can adapt this to your use case. And also, if you're more interested, you can check out the function, but it also checks that there's no like breaking layer between this layer and whatever the previous layer will be, because it works recursively. Like it goes all the way up until it finds a suitable candidate. But if there's like a breaking operation, like an add or an average pool or whatever, anything that's basically not a ReLU, it will say that that's not a valid candidate for CLE. But also, you might want to change this. Like I said, you might want to use different modules here. You might want to limit yourself to ReLU. You might want to put preLU or leaky ReLU in there. So yeah. Then these are the pairs that were produced. So like these two are going to have CLE done between them. These two are going to have CLE done between them. If we print out the entire graph, we can kind of see what this corresponds to. So like layer 1, 0, conv 1 is over here. We can see that it goes for a ReLU, and then it comes, and then the operation comes to this layer 1, 0, conv 2. So that makes sense. CLE is happening between those two. It's just a ReLU between the two. That's fine. But then between this layer 1, 0, conv 2 and this layer 1, 1, conv 1, there's a ReLU, which is fine, but there's also an add operation, which could break it. And so that isn't a valid candidate. So we see that we don't do CLE between like 1, 0, conv 2 and 1, 1, conv 1. So we don't do that there, but we do it between 1, 1, conv 1 and 1, 1, conv 2, because again, that is valid. It's just a ReLU between the two, which is cool. So it's working as expected. Here's just the PyTorch API for equalization. Cross Layer Equalization takes in the model, takes in the list of lists. It also has this threshold value, which kind of how stringent do you want to be about the Cross Layer Equalization. Then we just do our normal FX mode quantization. You could also do this in eager mode if you wanted to. At this point, it doesn't really matter. But yeah, just create the qconfigs, assign the qconfigs, torch, and get the model. I also wanted to compare, okay, what is the cross-layer equalized performance without, and then, without cross-layer equalization. So here we create another quantized model just without CLE. Same thing, we just create these qconfigs, we create the FX quantized model, and we fuse the batch norm into the conv, but we don't do CLE. Here we do our little evaluation. I do think I have to, because ResNet was trained and evaluated on ImageNet, and you can get the ImageNet data, you can get it off Kaggle. It's just really large. It's a massive data set. For my next video, I will do it. I will download the ImageNet, I will take a subset of that, and we'll use that for evaluating. Because currently I've always just evaluated on like a little samiad and a hen, because this isn't stuff I'm doing professionally. I pretty much only use ResNet as an example for these tutorials, but I will download ImageNet, I will take a subset, and then we'll actually have a proper evaluate function going forward. But yeah, here we just look at a picture of a dog, a samiad, and a picture of a hen. With CLE, we can see it does a little bit better. So in terms of, and these aren't world-breaking changes, but like 0.899 instead of 0.883, so it's a bit more confident than it's a dog than it would have been without CLE. Same thing with the hen, a 0.973 versus 0.972. Again, not world-breaking changes, but probably if you had a broader evaluation, you might actually start seeing differences. Something else I like to do is I'm a big visualization person. I like seeing my data. I originally have a data analyst background, so I like to view plots for stuff. And what makes the most sense in the case of CLE, in my opinion, is per channel box plots, because specifically it's supposed to operate on the dynamic ranges of the output channels of the weight tensors, so it would make sense that you would observe that. So there's just a little function to plot the per output channel box plots of a given weight tensor, but you can also save the plot if you want to. And you can do that, but I presumed you don't want to. But this is kind of what the plots look like. This is with cross-layer equalization. We can see that the dynamic ranges are more or less the same. Some are larger than others, but pretty much uniformly distributed. But then we can see without CLE, it's a lot more varied. Like we can see these outliers, and generally in the shape of the distributions, we can see that it's a bit more. I mean, probably not visible with the naked eye, but at least these outliers are pretty clear. Like, you know, those are there versus here, they're all kind of more uniformly distributed. Another plot I've created is the per tensor histograms with sensitivity analysis. This is something I created in my previous video, but by its nature, it's a per tensor visualization of what's happening. I've included this not because I think it's the right tool for this use case, but because I don't know what you, the listener or the viewer, is going to be doing with cross layer equalization. Maybe you have to go super deep on it, in which case I only give you all of the tools available that I have. But yeah, these are just kind of per tensor sensitivity analysis tools. I haven't plotted them because they take a while to, or I have plotted them, but I haven't put them in the notebook by default because they take quite a while to produce. But they look like this. Just a recap from the previous video, blue is the total distribution of the data, green is the sensitivity analysis, so if blue is the histogram, green is how much each histogram bin contributes to the final outcome of the model. This is with cross layer equalization, this is without. Maybe you're more keen than I am, and you're smarter and you can kind of like analyze this. You understand why this is the shape without CLE and this is the shape with CLE. I don't know why. But again, I just give you all the tools that you might need. But again, I think per channel box plots are what make the most sense here. And then printing out the quantization parameters. This is just another thing that you can do. I didn't do this for 0 points just because 0 points, it's symmetric quantization, so they're all 0 anyway. But yeah, here we just print out the scales and we can see that the scales tend to be smaller without CLE and they tend to be a bit larger with CLE. And I presume that the variance is actually smaller after you do CLE. But you can actually see that manifest in the box plots as well. Because like without CLE, the biggest value that we get is around 0.2. Without CLE, the biggest value that we get is about 0.3. So the dynamic range did increase with CLE, and that's something that manifests both in the plots and in the when we print out the quantization parameters. All right, that was it. That was it for the video. It was a quick one. Hopefully it was a useful one. As always, if you have any questions about cross-layer equalization or anything to do with quantization, by all means send me a message. The GitHub link is in the description. For my next video, I'm not sure. I'm not sure if I should do bias correction, which is the kind of second half of that paper, or move to like add around or AWQ, GPTQ. I'll maybe take a little bit of time to decide and figure out. But anyway, I may end up covering all of them, so it may not matter. But yeah, anyway, yeah, hope it was useful, hope it was interesting, hope you have a nice day, and I will see you next time. Subscribe if it's useful, press the like button, all of that jazz. Anyway, see ya, bye.